Hovercraft technology represents one of the most intriguing modes of transportation, enabling vehicles to move smoothly over surfaces like water, land, or even ice. This amphibious capability makes hovercrafts highly versatile and useful for rescue missions, military operations, and even recreational activities. The Landing Craft Air Cushion, or LCAC, is a high-speed, over-the-beach, fully amphibious landing craft used by the U.S. Navy and the Japan Maritime Self-Defense Force, capable of carrying a 60 to 75-ton payload. It transports the weapon systems, equipment, cargo, and personnel of the assault elements of the Marine Air-Ground Task Force from ship to shore and across the beach. An LCAC is essentially a hovercraft designed for military operations. It's designed to transport heavy equipment like tanks, artillery, and troops from ship to shore, especially in environments where traditional landing craft would be ineffective. At first glance, a hovercraft may appear to operate similarly to a helicopter. The dissimilarity between the two is in the balance mechanism. Both throw air down beneath themselves and ride on it. A helicopter utilizes its weight to balance, whereas a hovercraft uses a more straightforward and economical way, using less energy and fuel from the engine. The hovercraft engine propels a huge central fan facing down and smaller fans pointing rearward. The central fan provides an uplift to keep the vessel afloat from the waves, while the other fans move it forward, rearward, or sideways. Hovercrafts use rubber skirts to trap the air used to keep them afloat. 4 interacting components are at the heart of this rudimentary process. The hull provides the main structure and houses the cargo and machinery. The skirt system, arguably the most important component for puncture resistance, houses the air cushion. Lift fans force air under the craft to create and maintain the air cushion, while the propulsion system provides forward momentum. The skirt design represents the first and most critical line of defense against punctures. Early designs employed rigid skirts, highly susceptible to damage, and provided little flexibility upon impact with any obstacle. These early forays into making a viable hovercraft were plagued by durability issues, since even minor impacts could compromise the entire system. Indeed, the development of flexible skirt systems provided a real breakthrough in rapidly revolutionizing the industry and setting it up for modern, robust designs. By every definition, these skirts are true marvels of engineering, for they're made up of several layers of advanced materials. Neoprene-coated nylon is used for the primary layer due to its tremendous resistance to tear and environmental elements. This already versatile and resilient material is further treated with specialized coatings to enhance its resistance to UV radiation, salt water, and extreme temperatures. This also gives the neoprene coating a certain degree of self-lubrication that reduces friction if the skirt comes into contact with any other surface during its operation. Besides the base layer, modern skirts employ more layers of polyurethane-coated fabrics, which provide added strength while maintaining the flexibility required for the skirt's operation. These additional layers are placed so that they become increasingly flexible, with each layer typically performing one particular function in the overall performance. The outermost layer is usually sacrificial because it absorbs most of the impact from any contact with obstacles to maintain the integrity of the structural layers beneath it. The secret to puncture resistance lies in the multi-layer construction found in modern hover skirts. When an obstacle is encountered, the skirt does not oppose it but instead deforms, allowing the obstacle to push the flexible material inward without damage. This deformation is not a weakness in design, but rather, by design, a feature that will enable the hovercraft to pass over debris, rocks, and other obstacles. Projections without receiving punctures. The air cushion itself aids in returning the skirt to its original position, as continued pressure pushes the skirt back into its standard shape once the obstacle's been cleared. A second tier in providing puncture resistance is in constructing the hull. A modern hovercraft, similar to naval vessels, has been designed around the philosophy of multiple compartments so that the overall integrity remains intact if one area of the craft is compromised. The hull is generally of marine-grade aluminum or advanced fiber-reinforced composites chosen for their favorable strength-to-weight ratio and resistance to impact damage. Newer, larger, and more advanced models feature self-sealing in vulnerable areas using similar technologies to those applied to military aircraft fuel tanks. Such systems automatically deal with minor punctures before they can become serious problems. The self-sealing typically works via a special layer within the skirt or hull material which reacts chemically to air exposure. Consequence: when a puncture occurs, the material around the opening swells to block the breach, thus creating a temporary seal that can hold operating pressure until proper repairs are made. Another important principle in designing hovercraft is redundancy. Many critical components, such as lift fans and skirt segments, are duplicated to ensure that a single failure does not lead to the loss of the air cushion. Military hovercraft often work in very hostile environments, littered with objects that could easily cause damage. Puncture-resistant technologies continue to ensure the crafts remain operational. These vehicles need to be able to make landfall on beaches full of sharp rocks, move over ice fields, and remain operational even when potential combat damage occurs. Military hovercraft's success under such extreme conditions has driven many of the advances in puncture-resistant design that we see today. So, that was the end of the video. If you enjoyed it while watching, please subscribe for more content like this. See you in the next one.